Hello everyone. In this video, we are going to discuss one of the very basic topics of quantum mechanics, that is Schrodinger's equation. First of all, we will see that what's the actually need for Schrodinger's equation, and then later we will also derive the formula for Schrodinger's time dependent equation as well as Schrodinger's time independent equation. So everything about Schrodinger's equation we are going to learn in this video. So let's get started with this video. Okay, so our story begins in the year 1924 when Sir Louis de Broglie given his very famous de Broglie hypothesis. According to de Broglie, if there is a particle which is moving in a straight line, then we can associate one wave with that particle, right? So suppose this is one particle of mass m, it's moving this way, okay. So we can consider that this particle to be having wave nature also, like this. Okay. These waves which you associate with a particle, these waves are called matter waves. Okay. Now, when de Broglie hypothesis was given that we can associate one matter wave with a particle, then the next thing was that we had to find out the equation of this wave, right? See, every progressive wave has equation. So then next search begin to find out the equation of this matter waves. See, so we know that for any traveling wave, the wave which is traveling on the string or any in fact traveling wave, for that one equation is there, d square y by dx square equal to 1 by v square d square y by dt square. See, this is a classical equation for any traveling wave. If there is a wave which is traveling in one direction, let's say x direction, so that wave must obey this equation. It is in the classical physics, right? Now, this equation can have many solutions. For this equation, we can have this kind of a solution, or a cos omega t minus kx. Okay. Minus or plus, both are possible. Plus minus anything. We can have complex solution also for this equation, like a e power I is a complex number, omega t minus kx. Okay. We can also have I equal to a e power minus I omega t minus kx. So this equation can have any solutions out of this. Okay. Now the thing is here y represents some quantity. If you're talking about wave on a string, suppose there's a wave which is forming on a string. In case of wave on a string, this y represents displacement of the wave. It's a displacement of the wave. Okay, displacement of, you can say, particles of the string. If you are talking about electromagnetic waves, then electromagnetic waves, we know electric and magnetic fields are present. In that case, this y represents electric field, or this y may represent magnetic field. If you are talking about sound waves, then sound waves, this y may represents the variation in pressure, the changes in the pressure of air. So in different types of waves, the y represents different quantity. Sometimes y is a displacement, sometimes it's an electric field. So naturally one question came that if for these matter waves, this kind of an equation suppose we have, Schrodinger argued that for matter waves also these equations can be written. So one doubt came that for in case of matter waves, what this y represents actually? What will be in the place of y? In matter waves, y will not be a displacement or electric field or magnetic field. So in case of matter waves, what does y denotes? That was a problem. So later it was found that y denotes the wave function. In the place of y, wave function is written. Okay. Means in the place of y, wave function will be there. Now wave function is not directly measurable quantity. Okay, it's not having any measurable feature. So we believe that wave function is phi. It must be the complex nature. It is a complex function. So that's why we choose this equation for this. We believe that this is the equation for this matter waves. This one. Okay. First we'll start with this. We can write kx minus omega t, and we can also write omega t minus kx. It actually doesn't make any difference. Okay, here we can see that wave function is a depending on x and t both. So better we should write here x comma t. Okay. So we believe that this wave function is a complex thing. It's not any real thing like pressure or electric field. It's a complex number. So that's why we denote it this way. Okay. Now, okay. Clear? Now, this wave function which is there, phi. Okay. We can write in any format. Any format is okay. We can write reverse also. Just for making clear, I'll write reverse also. Whichever we like, we can choose it. Okay. Now, first of all, here omega, which is there. Okay. Omega is the frequency of this particle. Omega can be written as E by h stroke. This. Okay. Those who do not know this equation, we can derive it. Now, within a minute, I will derive it. Similarly, this k, which is there. Okay. K in this, it can be written as P by h stroke. P is a momentum, and here E is a kinetic energy or energy of the particle. Now, how do we got it? See, E is equal to h into frequency, we all know. Okay. So, if I here divide it by 2 pi and here also multiply by 2 pi, like this. H divided by 2 pi, this thing. H divided by 2 pi, it is written as h stroke. And 2 pi into frequency is the omega of the wave, E. From here we got that omega equal to E by h cross. Sometimes it is called as h cross or h stroke, we can say. It is basically h upon 2 pi. Similarly, if you want to see this derivation, so we know momentum is given by h by lambda. De Broglie hypothesis. It's momentum of a particle is h by wavelength. So momentum equal to h by lambda. Here if I again divide by 2 pi and multiply by 2 pi, the h by 2 pi it becomes h stroke. 2 pi by lambda is actually k equal to p. So that's why k we can write on as p by h cross. Okay. This one. Okay. Learn these things and make it clear. Okay. So this thing only I'm going to use here. In the place of omega, I'll write E by h cross. In the place of k, I will write p by h cross. So then same wave function equation, it become a e raised to minus I minus p x. And h cross I took common, it comes here. So this one I did. Okay. So first till this point you make it clear. Okay. Now we'll move further now. Okay, so after this, okay, let us now differentiate this equation. See, if you differentiate, but we have to go for partial differentiation because this wave function which is there, it depends on x and t both. Okay, so it's a having dependence on both variables x and t. So first we can take partial derivative of this with respect to x. Okay, let's take with respect to x first. Okay, so it will be like this. Del psi by del t, del x equal to here, okay, a derivative of this one would be same, et minus px. Then we are taking derivative with respect to x. Okay, so derivative of this p also will be there. No? So if you take derivative of this p, it will come p by h stroke. This also will come. Now again let's take derivative with respect to x. So it become double derivative, but take partial derivative, okay, with respect to x alone. Okay. Once you take here derivative again, okay, once you take derivative it will be I square p square h stroke square. Like this will come. Okay. Now over here, see this a and this part. Look at the underlined part. It is same as wave function phi. This we can write on as wave function psi. I square would be minus 1. So I square we write on as minus 1. P square by h stroke square equal to this one. Okay. Now this negative sign and h stroke square, let's pass it to other side. So we can write this way. Correct? Now dividing both sides by 2m, that's the mass of the particle. Dividing both sides by 2m. 2m is the mass of the particle. Okay, see, so this equation we are reaching, correct? Okay, let's give it some equation and leave it. Okay, this later will come across this. You might be knowing that p square by 2m is the kinetic energy of a particle. Okay, here p square by 2m we have to bring anyhow. It's actually kind of a kinetic energy of a particle. Okay, now keep it aside. Again, I'm writing wave function equation. Wave function x and t, it's a e power minus I, okay, divided by h cross et minus px. Right, wave function equation again. Now you take a derivative of this, partial derivative of course. Take a partial derivative with respect to time now. So it will be del psi by del t. Okay, a partial derivative we are taking. So this would come same. Okay. Now when you take derivative with respect to time, minus IE by h cross, this one will come. Okay, with respect to time we are taking, isn't it? So this is coming. Now over here also see it's a and e power this term, which is a and e power this term. For that we can write wave function psi. I can write this equation as del psi by del t equal to minus RE h cross psi. Yes. Okay. This we can write. Now both sides, if you multiply by minus I, okay, like this, so here become I square, right? Now I square is minus 1, that we know, it get cancelled, so you will get ultimately IH cross delta psi by delta t equal to E psi. Okay, this I square is minus 1, this minus and this minus get cancelled, so it will be IH cross del psi by del t equal to E psi. This is the second equation. Okay, so here this E that I am denoting, it denotes the total energy of a particle. Okay, but this p square by 2m usually denotes kinetic energy of a particle. Okay, first you learn this. Okay, now for this particle for which we are finding wave equation, suppose this particle is free particle, it's not bound with any force or anything. For a freely moving particle, okay, for this particle, kinetic energy plus its potential energy we can write down as total energy. The total mechanical energy would be sum of its kinetic energy plus potential energy. Okay. See, usually free particles don't have potential energy. That is also true. If particle is completely free from all forces, it don't have any potential energy. Okay. So freely particle, suppose it is particle is free, but it is bound by some forces, then it may have a potential energy. Okay. Okay. Sometimes we take this potential energy to be zero also, but while deriving, we'll keep potential energy. Now, kinetic energy, as we know, it's p square by 2m. Potential energy I am denoting by V symbol. Okay. Potential energy also, it may be the function of x and t both. Okay. And total energy, let's write down as E. Now, both sides, if I multiply by wave function psi, this. Okay. So the value of this p square by 2m psi, already we have found here, it is this much. Okay. That is minus h cross square by 2m del square psi by del x square plus V psi, E psi. The value of E psi we have found here, this one. This equation, can you see? This equation, at least we got from this only, simple energy conservation. It's actually based on conservation of energy. It is called Schrodinger's time-dependent equation, because here time term is there. This is only called as Schrodinger's time-dependent equation. Its equation is in one dimension because we are assuming particle is moving along x direction. Only it's an equation in one dimensions. See, if the particle is moving in 3 dimensions, okay, for that same equation can come minus h torque square by 2m. Okay, only it's del square by del x square which is there. It becomes this way. We'll take all x, y, z, all direction because particles moving in all direction. wave function psi, okay, plus v psi equal to again I h cross del psi by del t. Same, we can write this in 3 dimension. Now this operator which is there, this one, see this operator, this one, it is called as Laplacian operator. Okay, so it is denoted by delta square. This is Laplacian operator, so we can write it as delta square for this thing. Okay, so this is nothing but Schrodinger's time dependent equations. Now we'll derive the Schrodinger's time independent equation. Okay, so let's derive now Schrodinger's time independent equation. To derive time independent equation, we have to start with Schrodinger's time dependent equation only. So this is a time dependent equation that we just derived now. Now in this equation, this psi which is there, wave function, it depends on 2 variables, x and t, position and time. It depends on x and t both. So here we can use one mathematical concept which is separation of variables, method of separation of variable. According to this concept, this psi wave function which is depending on x and t both, it can be splitted into the product of 2 functions, let's say u and t. This we can written as product of 2 functions u and t. U will be the function of x alone and t will be, let's say, function of t alone. Okay, so these are 2 separate functions u and t which are depending on only one variable x and t. So wave function can be written this way. It is based on topic, that is method of separation of variables. We can separate this way. Now this thing, if I substitute over here, to see, minus h Stokes square by 2m. Here if I put this one, u and t both. Okay. In the place of this I am writing u and t. Okay. So since here you are taking derivative with respect to x, so t is considered to be constant, it goes out. It's only del u square by del x square, right? See, so here actually now since u depends only on x, u is a function of x only. So actually this partial derivative now we can write as an ordinary derivative also. We can write in the place of that ordinary derivative. Next step I'm going to do that. Here we can write ordinary derivative now. Okay. So u will come out as a constant, be derivative of t with respect to t. Now this t which is there, it is also a function of time only. So here also we can use like ordinary derivative. Okay. So first of all this one. Okay. In the place of this, I'm going to write ordinary derivative. Here also we can write simply ordinary derivative. Okay. Now if I divide both sides by this ut product, means if I divide both sides by a wave function, that is u into t. Here if we divide by ut, here also divide by ut, and here also divide by ut. So on that this t would get cancelled, here this get cancelled, and this get cancelled. Yes. Okay. What we are left with is minus h Stokes square by 2m, 1 by u, v. V is a potential energy, keep it in mind, IH cross. Now, so actually what we have done, now if you see left hand side of this equation, it is completely x dependent and the right hand side is only time dependent, t. Okay, all the time functions are on the right side and all the x functions are on the left side. We have separated this. Now look at the right hand side part, this one. Okay, this part we want to evaluate. We want to find value of this part. Now see, in the previous section we got one formula, if you remember this one, IH cross del psi by del t equal to E psi. Let us use this equation again. Okay, see, let's hold it here and write that equation first. IH cross del psi by del t equal to E. Okay. E psi, of course it is this way. Make it clear. This one I'm writing. Now, in this equation, if I substitute this psi as a u into t, here also u into t, okay, so u will come out of this derivative. U gets cancelled. Okay, so we'll get minus IH cross. This we can write down as the ordinary derivative because t is a function of only time. Written as ordinary derivative. Okay, and this capital T I shifted here. So I can say the energy of the particle is IH cross by T del T by del T. If you see this term, it's matching with this term. Okay, so in the place of this term we can write down as E basically. Okay. This term we can write down as E. V. No? Here we have minus H cross square by 2m 1 by U. This equation we got. Now, if I shift V this side, it become E minus V, and this term also completely shift on this side. So on just shifting all LH left hand side, on the right hand side you shift it, you'll get the equation H cross square by 2m 1 by U d square U by dx square plus E minus V equal to 0. This you're going to get if you put this all left hand side on the right hand side. See. Now just a few more steps. Okay, this equation we can rearrange and we can write this way: 1 by U du square by dx square plus 2m by h cross square, like this. Okay, the last step, now multiply both sides by u also, so we'll get finally du square by dx square plus 2m by h cross square to u. This u is a function of x alone, it is that u. Okay, so this equation that you are getting, see in this equation there is no term of the time. This is called as Schrodinger's time independent equation. Okay, see this, it's a Schrodinger's time independent equation. Okay, so here we discuss both types of equation. I hope you understood the concept. Soon we'll meet with the next video on next topic. If you have any queries in the modern physics or classical physics, any topic you want me to make a video, you can comment me on this email ID. We'll make video for you. Okay, till then, bye bye.